Question 1. Through the lens of a recent building retrofit, Mr. Carter notes that after upgrading the attic insulation, the indoor humidity levels unexpectedly increased. Given the HVAC BPA principles, what should be the most likely initial focus of investigation? A. Oversized cooling equipment. B. Lack of vapor retarder on warm side. C. Reduced natural ventilation rates. D. Incorrect refrigerant charge. Answer. Correct answer, C. Explanation. Increasing insulation can reduce air leakage, inadvertently lowering natural ventilation and trapping moisture indoors. This often raises relative humidity unless mechanical ventilation is adjusted. Oversized cooling can cause humidity problems but would likely have been an existing condition. Missing vapor retarders can allow moisture migration but not directly from insulation upgrades alone. Incorrect refrigerant charge affects cooling efficiency but isn't the primary cause of this specific post-retrofit humidity rise. ASHRAE 62.2 guidelines stress maintaining ventilation after tightening the envelope. Question 2. Given the circumstances, is Alvarez performs a blower-door test and finds the building leakage rate is significantly below the ASHRAE 62.2 minimum ventilation requirements. What is the most appropriate corrective action? A. Recommend partial removal of insulation to increase leakage. B. Install a balanced mechanical ventilation system. C. Increase the supply fan speed to create positive pressure. D. Reduce the use of combustion appliances. Answer. Correct answer, B. Explanation. When a building is too airtight, the solution is control mechanical ventilation to ensure consistent air exchange and IAC compliance. Removing insulation to increase leakage is counterproductive to energy efficiency. Adjusting fan speed for pressure control doesn't guarantee ventilation rate compliance or balanced airflows. Reducing combustion appliance use addresses combustion safety but doesn't ensure fresh air supply. Balanced mechanical ventilation aligns with ASHRAE 62.2 and maintains both energy efficiency and air quality. Question 3. By evaluating psychrometric data, Mr. Singh finds the indoor air at 75 degrees as dew point close to 65 degrees. Which problem is most likely occurring in the building? A. Excessive sensible cooling. B. Oversized cooling system with short cycles. C. High infiltration of outdoor dry air. D. Air leakage from return ducts into unconditioned spaces. Answer. Correct answer, B. Explanation. A dew point of 65 degrees indoors indicates high absolute humidity, often caused by oversized systems that cool the air too quickly without adequate dehumidification. Excessive sensible cooling doesn't directly explain the high moisture content. High infiltration of dry outdoor air with lower humidity. Return duct leakage from unconditioned spaces may add heat but wouldn't necessarily cause elevated dew point. Unless moisture is also present, is still the primary symptom here aligns with short cycling oversized equipment per ACAM Manual S guidance. Question 4. In light of recent developments, tighter building codes now require verification of duct leakage rates. During testing, Mr. Harris finds leakage to the outside exceeding allowable limits. What is the most efficient approach to address this? A. Increase blower speed to maintain air delivery. B. Apply mastic or 181 tape at all leakage points. C. Add return ducts to balance the system. D. Reduce total system airflow to mask leakage effects. Answer. Correct answer, B. Explanation. Properly sealing ducts with mastic or 181 compliant tape directly reduces leakage and improves efficiency. Increasing blower speed masks symptoms but wastes energy. Adding return ducts can improve balance but does not address leakage to the outside. Reducing airflow reduces comfort and system performance. Energy Star and DOE recommendations highlight sealing as the most cost-effective solution to meet leakage standards. Question 5. When analyzing combustion safety, is Reynolds measures a negative pressure of -7 pi in the combustion appliance zone during worst-case depressurization testing. What should be the immediate corrective action? A. Increase outdoor air supply to the zone. B. Relocate combustion appliances to interior space. C. Seal return duct leaks in the zone. D. Adjust exhaust fan operation schedules. Answer. Correct answer, A. Explanation. Excessive negative pressure increases backdraft risk. Supplying adequate outdoor air mitigates the pressure differential per BPA combustion safety standards. Relocating appliances may be impractical and costly. Sealing duct leaks can help but may not fully solve the depressurization issue if ventilation imbalance persists. Adjusting exhaust fan schedules can reduce depressurization temporarily but doesn't guarantee it under all conditions. Providing outdoor combustion air is the immediate and co-compliant solution. Question 6. Taking into account Mr. Patel's energy audit, he notes significant energy loss through poorly insulated ductwork in an unconditioned attic. Which recommendation aligns best with HVACR efficiency principles? A. Relocate ducts within conditioned space. B. Seal and insulate ducts to minimum R8. C. Increase supply air temperature. D. Install additional return grills. Answer. Correct answer, D. Explanation. While sealing and insulating ducts is important, adding return grills alone does not address heat loss. However, this question's trap is in assuming insulation is always first. Relocating ducts into conditioned space offers the most enduring efficiency improvement, reducing conduction and leakage losses, aligning with DOE and HVACR recommendations. Increasing supply temperature reduces comfort and system efficiency. Return grills improve balance but not thermal losses. Hence, relocation is most effective. Question 7. In the modern context of moisture management, Brooks observes condensation forming on interior window surfaces during winter. What is the most likely underlying cause? A. High indoor humidity with low window surface temperature. B. Outdoor infiltration, lowering indoor humidity. C. Excessive solar heat gain. D. Improperly sized furnace. Answer. Correct answer, A. Explanation. Condensation occurs when warm, moist indoor air contacts a cold surface below its dew point. High indoor humidity combined with poor thermal performance of windows causes this. Outdoor infiltration would usually reduce indoor humidity. Solar heat gain increases surface temperature, not condensation. Furnace sizing affects heating capacity but is not a direct cause of condensation on windows. Building envelope upgrades and humidity control per ASHRAE recommendations are key. Question 8. Based on the information gathered during IAC testing, ISTACHYM detects elevated CO levels in multiple zones during peak occupancy. What is the most appropriate corrective action? A. Increase outdoor air ventilation rates. B. Install FD lamps in the air handler. C. Replace HVAC filters with higher MERV rating. D. Reduce the thermostat set point. Answer. Correct answer, A. Explanation. Elevated CO indicates insufficient ventilation relative to occupancy, requiring increased outdoor air supply per ASHRAE 62.1. FD addresses biological contaminants, not CO. Higher MERV filters improve particle filtration but have no effect on CO. Lowering the thermostat set point changes comfort but not ventilation effectiveness. Ventilation adjustment is the direct, standards-compliant solution. Question 9. To better understand refrigerant management, Foster evaluates a system operating with subcooling far above manufacturer specifications. What is the most probable cause? A. Undercharged system. B. Overcharged system. C. Low indoor load conditions. D. Non-condensable gases in the system. Answer. Correct answer, B. Explanation. High subcooling indicates liquid refrigerant overaccumulation in the condenser, typically from overcharging. Undercharging results in low subcooling. Low indoor load can affect pressures but doesn't inherently cause excessive subcooling. Non-condensables increase head pressure but generally reduce subcooling. Following manufacturer charging charts and EPA Section 608 best practices prevents such overcharge conditions. Question 10. From a practical standpoint, Mr. Lopez assesses a commercial rooftop unit where uneven airflow distribution is causing hot and cold spots. Which approach most directly addresses the root problem? A. Balancing the duct system using an airflow hood. B. Increasing the overall system airflow. C. Adding zoning dampers without measurement. D. Replacing supply registers with high throw models. Answer. Correct answer, A. Explanation. Balancing the duct system ensures each zone receives correct airflow per design, directly resolving distribution issues. Increasing system airflow without balancing can worsen imbalances. Adding dampers without measurement risks over or undersupplying certain areas. High throw registers can improve mixing but don't address the root imbalance. A CAT manual D and tab best practices emphasize systematic balancing as the first corrective step. Question 11. When faced with a large office retrofit, his Grant finds that after installing low-E windows, summer cooling demand dropped, but winter heating costs increased slightly, at which building science principle best explains this. They reduced solar heat gain in winter, B. Low-E value of glazing, C. Increased infiltration due to frame shrinkage, D. Thermal bridging at mullions. Answer. Correct answer, A. Explanation. Low-E coatings block infrared heat transfer, reducing cooling loads in summer but also limiting beneficial solar gains in winter, increasing heating needs. Low-E value improves insulation year-round and wouldn't cause heating increases. Frame shrinkage and infiltration are unrelated unless window installation was defective. Thermal bridging at mullions can increase heat loss but wouldn't be direct result of Low-E change. Building performance analysis must weigh seasonal trade-offs per HRConquer energy modeling practices. Question 12. The impact of ventilation imbalance is seen when Mr. Delgado observes his facility's indoor air pressure is slightly positive year-round. What is the most likely direct consequence? A. Reduced infiltration of outdoor pollutants. B. Increased exfiltration and energy loss. C. Reduced latent cooling load. D. Higher co-levels during occupancy. Answer. Correct answer, B. Explanation. Positive pressure pushes conditioned air out through leaks, increasing exfiltration and wasting energy, particularly in heating or cooling seasons. Reduced infiltration of pollutants can be a benefit, but the primary measurable issue is energy loss. Reduced latent cooling load is not directly linked to pressure differences. Co-levels relate to ventilation quantity, not pressure direction alone. Pressure control should be to minimize both infiltration and exfiltration while meeting IAC needs per HRConquer 62.1. Question 13. To determine whether moisture intrusion is occurring, O'Neill uses thermal imaging camera during humid summer afternoon. Which signature most likely indicates an active moisture problem? A. Cooler than surrounding area with consistent temperature pattern. B. Warmer spots surrounded by cooler surfaces. C. Random fluctuating temperature spots. D. Cooler area following structural framing lines. Answer. Correct answer, A. Explanation. Active moisture often evaporates, causing localized cooling visible as a consistent cooler pattern in thermal imaging. Warmer spots could indicate heat sources, not moisture. Random fluctuating spots may be artifacts or air currents. Cooler lines along framing often indicate thermal bridging, not moisture. Thermal imaging per atom C should be paired with moisture meters to confirm active problems. Question 14. In summary of a performance test, Mr. Howard finds the cooling coil temperature differential is significantly lower than design. Which condition is most likely responsible? A. High outdoor humidity load. B. Insufficient refrigerant charge. C. Excessive airflow across the coil. D. Dirty return air filters. Answer. Correct answer, C. Explanation. Excessive airflow reduces contact time between air and coil, lowering temperature drop. High outdoor humidity increases latent load but may not reduce coil DT if properly sized. Insufficient refrigerant usually increases superheat but lowers capacity overall, not matching the symptom exactly. Dirty filters restrict airflow, increasing DT rather than lowering it. CAM manual S and service diagnosis. Emphasize airflow verification before refrigerant adjustments. Question 15. A critical examination of combustion analysis in Mr. Ward's boiler shows high co-levels and low flue gas temperature. What is the probable primary cause? A. Excess combustion air. B. Blocked heat exchanger passages. C. Underfiring of the burner. D. Incorrect vent sizing. Answer. Correct answer, B. Explanation. Blocked heat exchanger passages trap flue gases longer, cooling them and potentially creating incomplete combustion that raises CO levels. Excess combustion air generally lowers CO by improving burning efficiency. Underfiring reduces flue temperatures but doesn't inherently raise CO unless combustion is poor. Incorrect vent sizing affects draft but not directly both CO and low flue temps simultaneously. NFPA 54 and BPA combustion safety procedures require prompt correction of blockage issues. Question 16. From multiple perspectives, Lewis evaluates a mixed-use building's rooftop unit and notes frequent compressor short cycling during mild weather. What operational change is most appropriate? A. Add low ambient control to condenser fans. B. Reduce evaporator airflow. C. Implement staging or variable capacity control. D. Increase thermostat deadband. Answer. Correct answer. C. Explanation. Staging or variable capacity allows the system to match load during mild conditions, preventing short cycling and improving efficiency. Low ambient fan control addresses winter operation issues, not mild weather cycling, reducing airflow risks, coil freezing, and inefficiency. Increasing thermostat deadband can help slightly but doesn't resolve capacitor load mismatch, though efficiency guidelines support load matching controls. Year-round performance. Question 17. Examining the consequences of infiltration, Estepans notes that during winter incoming air feels unusually dry. What is the primary reason for this perceived dryness? A. Outdoor air having low absolute humidity. B. Building's heating system overdrying the air. C. High ventilation rates exceeding design. D. Poorly insulated walls increasing surface cooling. Answer. Correct answer. A. Explanation. Cold outdoor air naturally has low absolute humidity. When heated indoors without moisture addition, its relative humidity drops significantly, causing perceived dryness. Heating itself doesn't remove moisture beyond lowering relative humidity. Excessive ventilation can worsen the issue, but it isn't the fundamental reason cold air is dry. Poor insulation affects heat loss, but not humidity content directly. ASHRAE winter humidity control strategies address this. Question 18. Contrary to popular belief, increasing insulation thickness in a humid climate without ventilation changes can lead to which unintended issue? A. Low cooling energy use. B. Reduced indoor humidity. C. Trapped moisture within assemblies. D. Increased conductive heat loss. Answer. Correct answer. C. Explanation. In humid climates, more insulation can reduce drying potential by lowering surface temperatures inside assemblies, trapping moisture if ventilation and vapor control are inadequate. Low cooling uses a benefit, not an issue. Reduced humidity is unlikely without dehumidification changes. Conductive heat loss decreases with more insulation, not increases. Proper hydrothermal design per ASHRAE 116 ensures insulation doesn't cause moisture problems. Question 19. Throughout the course of a duct blaster test, Phillips measures total duct leakage at 20% of system airflow. What is the best practice next step? A. Replace all ductwork immediately. B. Identify and seal leaks with mastic or 181 tape. C. Increase fan speed to compensate. D. Add insulation to ducts. Answer. Correct answer. B. Explanation. Sealing leaks to bring leakage within code limits is the most cost-effective and performance-improving step. Total duct replacement is costly and unnecessary unless ducts are severely damaged. Increasing fan speed masks the problem but wastes energy. Insulation addresses conductive losses, not leakage. EPA and Energy Star emphasize sealing before insulating for maximum benefit. Question 20. As a result of an IAC investigation, Istatana finds elevated VOC levels in a new commercial building. What is the most effective immediate mitigation strategy? A. Install activated carbon filtration in the HVAC system. B. Reduce ventilation to maintain pressurization. C. Seal ductwork to prevent leakage. D. Increase mechanical ventilation rates temporarily. Answer. Correct answer. D. Explanation. Increasing ventilation temporarily flushes VOCs from new materials until off-gassing diminishes in line with ASHRAE 62.1 and LEED guidelines. Activated carbon can help but is less effective for high initial VOC loads. Reducing ventilation worsens indoor pollutant concentrations. Duct sealing improves efficiency but doesn't address VOC levels directly. Ventilation purging is the immediate standards-based approach. Question 21. From a historical standpoint, Mr. Daniels inspects a 1960s commercial building with single-pane aluminum windows. He notices strong downdrafts near the glass during winter. What is the main physical process causing occupant discomfort? A. Radiant heat loss to cold glass. B. Excessive air infiltration through window seals. C. High convective heat transfer near glazing. D. Thermal bridging through framing. Answer. Correct answer. A. Explanation. Cold glass surfaces cause occupants to lose radiant heat, creating discomfort even when air temperature is adequate. Infiltration may be present, but the main sensation is radiative cooling. Convective heat transfer contributes slightly but is secondary. Thermal bridging increases conductive losses, but does not fully explain the downdraft sensation. ASHRAE thermal comfort standards highlight radiant effects as key to perceived comfort near large cold surfaces. Question 22. Taking into account IAC readings, is Roberts observes CO levels consistently 1200 ppm during peak occupancy despite the HVAC system meeting design airflow rates. What is the most probable explanation? A. Damaged duct insulation causing temperature drift. B. Incorrect occupancy assumptions in design. C. Excess outdoor air infiltration. D. Leak condensate drain allowing odors in. Answer. Correct answer. B. Explanation. If designed ventilation rates are based on underestimated occupancy, actual cogeneration will exceed design expectations, causing higher levels. Damaged insulation affects thermal comfort but not CO. Outdoor air infiltration would typically reduce CO. Leak condensate drains may cause odor complaints but not elevated CO. ASHRAE 62.1 emphasizes accurate occupancy estimates in ventilation design to avoid chronic IAC issues. Question 23. By comparing summer and winter energy bills, Young finds summer consumption is significantly lower after installing a white reflective roof, but winter costs slightly increased. What building science principle explains this? A. Reduced roof emissivity in winter. B. Reduced solar heat gain year-round. C. Increased roof air leakage. D. Greater radiant heat loss to the sky. Answer. Correct answer. B. Explanation. Reflective roofs reduce solar heat gain in all seasons. This is beneficial in summer but eliminates helpful gains in winter, leading to slightly higher heating loads. Reduced emissivity would lower winter losses, not raise them. Air leakage changes are unlikely from roof surface change alone. Radiant heat loss to the sky remains similar unless emissivity is altered. DOE-Cool roof guidelines note this trade-off in colder climates. Question 24. Throughout the course of commissioning, a new ERF system ISTA Ortiz detects that multiple indoor units are operating at lower capacity than expected under partial load. Which adjustment is most likely to resolve the issue? A. Resetting refrigerant charge to manufacturer specifications. B. Rebalancing ductwork airflow to each zone. C. Updating control settings for diversity management. D. Cleaning outdoor heat exchanger fins. Answer. Correct answer. C. Explanation. ERF systems rely on control logic to allocate capacity among indoor units. Incorrect diversity or priority settings can limit certain zones' capacity. Refrigerant charge errors affect all units more uniformly. Airflow balancing applies to ducted systems but may not address ERF refrigerant control logic. DESI coils reduce heat transfer but would impact full load performance as well. Manufacturer control commissioning guidelines are key to VRF optimization. Question 25. The conventional wisdom about heat recovery ventilation HRV is that it always saves energy, but Mr. Fisher's cold climate audit shows higher heating bills after HRV installation. What is the likely cause? A. Poor defrost strategy increasing runtime. B. Inadequate filter maintenance. C. Incorrect duct sizing in return branches. D. Excess ventilation rate beyond design. Answer. Correct answer. D. Explanation. HRV can increase heating costs if ventilation rates exceed design, bringing in more cold outdoor air than necessary. Poor defrost strategy may reduce efficiency but not cause sustained high heating load unless extreme. Dirty filters cause airflow issues but not significantly higher heating bills. Incorrect duct sizing affects balance but not overall heating energy unless causing major overventilation. Commissioning per ISAF ensure HRV rates match design intent. Question 26. Despite the fact that ISTA Coleman improved attic insulation, occupants still complain about summer overheating in upper floors. Which factor is most likely still unaddressed? A. Inadequate soffit to ridge ventilation. B. Excessive latent heat from appliances. C. Insufficient shading on south-facing glazing. D. Improper refrigerant metering device setting. Answer. Correct answer, C. Explanation. Solar gain through unshaded glazing can cause overheating regardless of insulation levels. Attic ventilation reduces heat buildup but may not solve solar gain from windows. Latent heat from appliances affects humidity more than temperature. Refrigerant metering settings impact cooling equipment efficiency but not passive solar gain. Building performance assessments per DOE guidelines prioritize solar control measures for upper-level overheating. Question 27. When evaluating the merits of duct sealing, ISTA Blake notes that return duct leaks from an unconditioned attic can cause which primary effect? A. Reduced building infiltration rates. B. Depressurization of conditioned space. C. Increased supply air temperature. D. Improved coil latent performance. Answer. Correct answer, B. Explanation. Return leaks pull attic air into the system, causing conditioned space to depressurize, which can increase infiltration of outdoor air elsewhere. This degrades efficiency in IAC. Reduced infiltration is the opposite of what occurs. Supply air temperature is typically reduced, not increased. Coil latent performance may be altered but usually worsens due to increased load from warm, humid attic air. Duct dyne. Emphasize sealing returns in unconditioned spaces first. Question 20. From a practical standpoint, Morgan is tasked with improving a grocery store's refrigeration system efficiency, which upgrade yields the most consistent year-round savings. A. Installing floating head pressure controls. B. Increasing condenser fan speed year-round. C. Oversizing evaporators for lower coil temperature. D. Reducing defrost cycles to the minimum. Answer. Correct answer, A. Explanation. Floating head pressure controls adjust condensing temperature to outdoor conditions, significantly reducing compressor energy use year-round. Increasing fan speed increases energy use. Oversizing evaporators can improve performance but raises capital and defrost energy costs. Reducing defrost cycles too much risks frost buildup and performance loss. DOE refrigeration efficiency case studies highlight floating head pressure control as a key retrofit. Question 29. The effectiveness of air sealing strategies is evaluated in a high-rise apartment with persistent odor transfer between units. Which sealing location has the highest priority? A. Exterior wall penetrations. B. Shared ductwork between units. C. Electrical and plumbing chases between units. D. Window frames. Answer. Correct answer, C. Explanation. Vertical chases often create strong air pathways between units, allowing odor and contaminant transfer. Sealing these has the greatest IAC impact in multifamily buildings. Exterior penetrations improve envelope performance but not unit-to-unit odor control. Shared ductwork is typically addressed by system design changes, not sealing. Window frames affect infiltration from outdoors, not inter-unit movement. ASHRAE multifamily IAC guidelines prioritize sealing internal chases first. Question 30. Across different scenarios, ISTA Allen compares commissioning results for two similar buildings. One shows lower than expected airflow despite correct fan settings. What is the most likely cause? A. Excessively high duct static pressure from restrictions. B. Incorrect motor pulley alignment. C. High indoor humidity affecting fan blades. D. Overventilation through operable windows. Answer. Correct answer, A. Explanation. High static pressure from undersized ducts, dampers, or blockage reduces delivered airflow even when fan speed is correct. Pulley alignment affects belt-driven fans but less commonly causes large airflow deficits without noise or vibration. Humidity does not significantly change fan blade performance. Overventilation through windows changes room pressurization but not measured fan output during commissioning. Counterbalancing procedures stress verifying static pressure first.